I am Sebastian Michelmann. I am a postdoc at Princeton, and I did my PhD in Birmingham, UK, where I was supervised by Simon Hasselmeyer and Howard Bauman. Today I want to show you some highlights from my thesis, which addresses the question of how we reinstate information-rich, dynamic memory content that unfolds in our memory over time. To give you an intuition on this, maybe think of the last movie that you've seen in cinema before this pandemic started. And if I ask you now about your favorite scene in that movie, you're probably able to reinstate a temporally accurate representation of dialogue and events in front of your mind's eye. On the other hand, if I ask you, what else did you like about this movie, you can probably answer this question without zoning out for almost 2 hours. And this implies that we can somehow do both. We can re-experience temporally accurate information, however, we can also somehow skip through our memories at a faster speed. And later in this presentation, I want to show you evidence for both of these phenomena. In the example that I just showed you, I wanted to stress that our experience unfolds over time. Temporal structure, however, is also something that is inherent to our nervous system. So just like our hearts beat rhythmically, our brains are also marked by rhythmic fluctuations of neural activity that we can measure with electrophysiology. Most prominently, the alpha rhythm around 10 Hertz is something that we can even see in the raw EEG sometimes. Historically, the alpha rhythm was long thought of as a marker of an inactive brain. So the idea was that the brain basically goes into this oscillating state when it's doing nothing. But this idea was then superseded by the observation of a functional role of alpha in the inhibition of irrelevant information. So instead of being idle, our brain actually ramps up the strength of alpha oscillations in order to suppress irrelevant information. And today we have even more evidence for the functional role of alpha. And I want to highlight here the observation that attention actually seems to rhythmically sample our continuous experience in the lower alpha band when we perceive information. And another interesting observation is that synchronous high alpha amplitude is actually bad for the representation of complex information in the brain. And the logic here is that if neural assemblies are all firing in synchrony, this amounts to a lot of redundancy. So almost like a flip side to this inhibition hypothesis, the information via desynchronization hypothesis highlights that in order to represent complex information in the brain, neural assemblies need to be somewhat desynchronized. Therefore, in order to represent complex information, our brain needs to, in our brain, we actually need alpha power to go down. And this latter idea gives a straightforward explanation of one of the most ubiquitous phenomena that we observe during successful memory encoding and retrieval, namely the strong decrease of amplitude in the alpha and beta frequency band. So here I'm showing you an example of this. When subjects see a word cue and successfully remember an associated video clip, we can see the strong sustained power decrease that is most pronounced in the lower alpha band. And if you're not familiar with this kind of plot, you see time on the x-axis, frequency on the y-axis, and color typically codes the strength of the signal, the amplitude. And specifically here, color codes the codes t values that mark the association of power decrease with successful memory reinstatement. So in line with this idea that desynchronization of neural assemblies marks the processing of rich stimulus information, in studies from my PhD, we could show that these decreases in power during reinstatement harbor temporal patterns of activity that are specific to the stimulus that is being remembered. What I want to show you now in the rest of this presentation is a study in which we used the tracking of alpha oscillations in order to understand the unfolding of continuous video content as it is reinstated in a purely memory-driven way. Specifically, we designed a cued recall paradigm here in which we used a specific type of stimuli. So these stimuli, which we call video episodes, are 6-second long videos that consist of 3 distinct scenes. And importantly, in one of these scenes, a unique word cue will appear in the center of the screen. So here you see one of these video episodes, a ship sailing by, a diver jumping into the water, and then an octopus floating. And if you paid close attention, you could see the word apple appear there in the second scene of this video episode. So these 4 different video episodes were repeatedly paired with distinct trial unique word cues during encoding, and our participants had to learn to associate these word cues with each of these respective scenes. Later during retrieval, we could then show this unique word cue and ask participants, in which exact scene did you see this word? And the idea is now that in order to answer this question correctly, people will have to evoke a vivid representation of this video episodes in front of their mind's eye in order to find the correct response. And importantly, if we go through these video episodes in a forward direction in a memory, this would mean that we should arrive at the first scene before we arrive at the second and at the third scene. And we tested this prediction in a behavioral experiment where we asked our participants to make this selection as quickly as they can. And what we see then is that participants are actually much faster to retrieve associations that were learned in the first position compared to the second and compared to the third position of the video episode. And this modulation of reaction time with position speaks for a forward replay mechanism. And there's another observation here, which is that the time it takes to, in the actual video episode, to get from scene 1 to scene 2, namely 2 seconds, is actually much longer than the reaction time differences that we observe here in the behavioral results. And if we compare them directly, we can see that the reaction time differences are about 14 times shorter than the duration of the video episodes. Therefore, we could say that memory replay proceeds at a compressed speed that is about 14 times faster than the original perception. The interesting question is now if we can track these representations in memory as they unfold over time. To do this, we did an MEG study where we fixed reaction time, the time to respond to 3.5 seconds. And again, subjects would associate unique word cues with positions within these scene positions within these video episodes. And later during retrieval, we would ask first, in which scene did you learn this association? And then ask our participants to also confirm the exact video episode. And if somebody has this scene position and the video episode correct at a given trial, we would mark this trial as a hit. Now, the interesting part is here to track the temporal patterns from encoding that we observe during perception of these video episodes later as they unfold in memory during this retrieval interval of 3.5 seconds. So in order to track these temporal patterns in the alpha band, we now reconstructed our virtual electrodes on an occipitoparietal region of interest of virtual electrodes, as we can do with MEG. And now we computed the phase coherence over time between all 1-second windows from encoding and all time points from retrieval as a similarity measure. And if we have a similarity measure, we can use representational similarity analysis to compare pattern similarity, for example, between watching movie A, remembering movie A, watching movie B, and remembering movie B. And then we can shuffle and compare instances of different perceptual and memory content. For example, watching movie A, remembering movie D. And this contrast of combinations of similarity between combinations of same perceptual and memory content and different perceptual and memory content gives us the ability to contrast for content-specific pattern reinstatement in memory. So when these associations were remembered, we found a cluster of content-specific reinstatement of temporal patterns from these video episodes in this occipitoparietal region of interest. On the other hand, when we did this for trials in which the association was forgotten, we did not observe this pattern reinstatement. And crucially, this difference between the two is also a significant one, thereby linking this pattern reinstatement to the successful memory reinstatement. Now that I've shown you that temporal patterns in the alpha band reappear, you may want to know in which order. So do earlier patterns from the video episodes also come back early into memory, and do later patterns also reappear later? So to answer this question, we divided the video episodes into 6 non-overlapping windows and assessed when patterns within these windows reappear. So to do this, we can inspect the distribution of evidence that we find during retrieval. Specifically, we can check at every time point how much evidence for each of these windows have we found. So you can imagine this as a race. Like if we accumulate this evidence, if there is more evidence for window 1 over window 2, we would say that this window is leading over the other and the other is lagging behind, thereby establishing an order of replay here between these two windows. And now we estimate this lag across all these 6 windows at every time point during retrieval. And what we find is that this lag is statistically negative, such that we find significant negative lag of replay throughout the retrieval interval. And what that means is that early patterns also come back earlier into memory, and late patterns come back late into memory, that thereby indicating a forward direction of memory replay in the neural data. So behaviorally and neurally, we can therefore establish memory replay as proceeding in a forward direction. You might now think that I've shown you some contradictory results. So on the one hand, I showed you that replay is compressed. On the other hand, I showed you that we can detect content-specific temporal patterns in memory, indicating replay at the same speed. So how does it fit together? Somehow, our brain must be able to do something like a CD player, where it can skip ahead between tracks, but it can also listen in on detailed memory traces. And the way we designed our experiment, the boundaries between these scenes are actually somewhat salient elements. So if we do indeed skip between elements, then we hypothesized that it should be more likely that we skip to the beginning of a new scene than skipping to any random moment in this video episode. And this makes a straightforward prediction, namely that if skipping can actually help us to speed up our replay process, then if we only focus on the patterns that are within the same scenes and try to estimate the speed of replay only within scenes, then we should underestimate the speed. Because remember that skipping to the beginning of a new scene can help you speed up. Then if we just ignore these skips, we should underestimate the speed. To be more specific, if we have a very strict forward replay model where the memory replay is just a recapitulation of the original experience, we would expect a pattern like this, where this negative lag indicating forward replay just linearly increases with every subsequent window within these video episodes. So every following window should just increasingly lag behind the earlier ones. On the other hand, if we do oftentimes skip ahead, we would expect that such a flexible pattern where the lag within these, so the lag of patterns that belong to the same scene should actually be much more negative than the lag of windows that do not belong to the same scene. And we can quantify this directly or test this statistically directly by comparing the speed of replay that we find when we only focus on patterns within scenes compared to the overall speed of replay. And what we find is indeed that the local speed of replay is significantly slower than the overall compression level permits. And if we measure this directly by comparing these distributions in in time, we also find a pattern that is more consistent with this flexible forward replay model than with the strict forward replay model. So in conclusion, I hope I could show you that the replay of temporal patterns in the alpha band is associated with successful memory retrieval, and that replay is compressed, that it's forward, but it's also dynamic. So the skipping between sub-events seems to be faster than the replay within scenes. And finally, I want to make the statement that replay of episodes is more than just the exact recapitulation of the original experience, and somehow dynamic processes must be at work. Then we can track those by using, for example, oscillatory pattern similarity, as in this study. Then I want to thank everybody from Birmingham who supported me in my PhD, and first and foremost, of course, my two supervisors, Howard Baumann and Simon Hanselmeier, who have been an incredible source of support throughout these years.